The topic of this lecture is a question, and question is about electron, that can one electron pass through two slits. I should clarify that electron is just an example, and slits are also make an example. Actual underlying question is that according to quantum mechanics, can a particle, it may be electron or maybe any other particle, can simultaneously pass through two different tracks, two different paths? And the answer is in quantum mechanics, and the meaning of the answer in standard quantum mechanics is equivalent to that yes, a particle can pass through, but the crucial word is pass through. When it is passing, it's a probability wave, and wave can pass through many paths. You have a water wave, and you can see that it goes through many paths. It's not only two, it can be any. So two, yes, it's a wave, but you have to remember it's not a water wave, actually it's a probability wave. And probability wave is a measured like a dice probability. See, you have to see events, and you say ratio of events, and events a dot, and dot is like a particle. That's why it's called particle. Now in this slide, in this lecture, what you say, I have to show you two different sorts of scene. Scene is like a measurement. One is only a wave where wave strikes. We see it only there when it strikes. Another experiment is that during motion, when it's passing through here, we also detect it. Now there are just two ways of seeing. Now some people think scene is actually a human activity. So some people make it a fancy situation out of it, and you say that it's a quantum mechanics has any interaction, as in something special about human activities. That is not what quantum mechanics is. It's not necessarily that scene is by consciousness or human being or any mind or anything. Not necessarily. What matters is interaction. If you have a wave, and remember electron is a wave, and it interacts by us, by our apparatus, or by another particle sent by us, or it may be anywhere, maybe in a far galaxy where there is no consciousness, there is nothing, anything, a wave is there and it interacts with another wave. So waves are modified. So interaction can be in any way. You know, this here it is seeing at screen, seeing during motion, seeing by human being or not. There are different ways of interacting waves. So it's the what matters is interaction. So that is the topic of topics of this lecture. And the last is that the effects of, now I think I would like to use interaction, not seeing or things like that. The effects of interaction, you may still like to use the word scene, but I would prefer interaction. Whatever you say, whatever effects, they are irreversible. And that is called wave function collapse. I have to explain when it comes. So that's all outline of that, and now I start with first thing in detail. And that is, I've talked about wave. The question is what is wave? In general, it can be said that it's the same answer, but at least in case of electron or so atom, where you can't see that in the world of electron or so, only our mathematics is relevant. So at least for that justification, you say wave is to be described by mathematics, and mathematics is wave equation, and wave equation has changes with position and changes with time. And here you can see this wave is changing with time and is changing with position as well. Now these waves, or any waves, they obey a principle which is called principle of superposition. That means they can enhance each other. They rise and fall together and they become double. That is the constructive interference. They can cancel each other. This is destructive interference. Whatever it is, maybe something else, not constructive, not destructive, something intermediate. Whatever it is, this solution, this sum is also a wave. Now, when I say also a wave, I mean is also a solution of the same wave equation. You know, it's a simple mathematics you can do yourself. Here on psi you put subscripts 1, psi 1, this equation is there, you write equation, you write for psi 2 and you add up, that's it. So that means the sum is called superposition, and that's one example of superposition. The superposition can be more general or more complicated, that's coming in next lectures. But whatever is superposition, that's an example of it. That is also a wave, that is also a solution of the same differential equation, same wave equation. Now that this wave has a pattern, different two patterns I have shown, it can be any pattern. Now, since by quantum mechanics probability density is related to wave, and that is there, probability density is the wave function square, and square is you multiply with complex conjugate. I have told you that a benefit of that is that it becomes, even if it is a solution is a complex number, the result becomes real non-negative, you can say positive, like the probability is. So if it's a pattern in a wave, is there a pattern in probability density? Answer is yes. I show mathematics if you are interested. You bear with me for 2-3 minutes, otherwise just wait for a result which should be in 2-3 minutes and you see only result. But for those of you who want to know, I describe some detail. And details are the following. Psi, that can be a complex number, actually it varies with position and x, so I would say complex variable. Now, whether it's a complex number or complex variable, that has a real part, that has imaginary part, and you can make a picture in which trigonometry would allow you that your this real part is magnitude cos theta, theta is there, that's a simple trigonometry, and the vertical is magnitude into sine theta. Now that Euler formula says that becomes z bar e bar iota theta. Now here I have modified theta by delta because that is the symbol used in quantum mechanical probability pattern recognition and so on. So you have to bear with me with if you say suddenly sign change. It's the same thing, it's different names, symbols are given. And what happens is that this mathematics we apply to psi 1, so that means the magnitude is psi 1 mod magnitude, and delta is that, and you apply to psi 2, and now here you substitute this result, psi 2 you substitute this result, here is the same, you say complex conjugate iota will become minus iota, and this will become minus iota. All in all you do sum, and I think for physics what you may be interested is only a result, and result is the following. If you put 2 in 1, that this is a pattern, this is a formula. You need not understand all the detail of what it is. The crucial thing to be noted is this is a pattern, this is a formula which is not random, but the probability has some relation to the randomness. Now what it is, I recall what is probability, and the thing is like a coin. Probability is seen in this way, that if you have a large number of tosses, here actually is not toss, what I mean to say is large number of detection. I'll show you what detection is, but first you revise what is the probability, how probability is seen. There are two conditions to be fulfilled before you decide it's a probability, and that is that for large number of experiments, detection, tosses, whatever you call it, probability becomes proportional to number of experiments you have done. Experiment maybe a toss starting with, if both sides have 50-50% probability, that means both sides have equal number of appearances. Here appearances will be a different form, but the general rule survives, that number becomes proportional to probability. So if you have a formula for probability density, it becomes the same formula because proportionality constant cancels throughout, and the same formula is applied to numbers. A number of what? I tell. But before that, you remember, only that much is not sufficient to say it's a probability, because that may be a result of a strict mathematics. But if it's a probability, there should be some randomness, and that is randomness in when the number of experiments are small. For a dice, if you don't throw away large number of times, then you know there's no pattern. It may be heads may appear 20%, 30%, 70%, any. That's for small number. Now, so far I've been saying dots, dot. Now I tell you what is actually here. We are not talking about, I've been saying about toss, but actually here in quantum mechanics, we are not talking about tosses. We are talking about, let me show you, we're talking about dots. Now, quantum mechanics says, when you wait for it, that when there are a large number, it's a pattern. A pattern is there. And when it's a small number, I show you once again. When it's a small number, I just waited now. Here is a small number. You say no pattern. So this combination, no pattern and then pattern, that is the signature of probability. Now, if you're wondering, this is obviously not toss. This is not dice. What experiment is? I just tell you that's the topic of next slide. An experiment is the following, which is called double-slit experiment, in which you have a source, which is, for next slide I will need to say that this is source of electron, but it can be a photon. Photon means light, electron means, hopefully you start getting used to, electron is electron. It's called electron gun. If it is a photon, that would be ordinary bulb, but here I mean it's electron. I need for next slide to be this electron source. Now the crucial thing is that in this slide, we are talking about first experiment. Here the detection is only on screen. So there is no detection, no seeing the path. So people who make any picture about the path, I think, and they show that, I mean, I have shown it in my thumbnail, but I have put a question mark with it. But if you don't put question mark and you say you show a path, I think that is logically imperfect. When you have not seen a path, you don't know anything about path. That's it. Practically, it's the same situation with bullets as well. You see only where bullets strike practically, but it's only practically. In principle, you can think of that bullets, we know the path. But here, if you have not seen it, we don't know. Even not in the sense of bullet, nothing. But that is as far as our observation says. But theoretically, quantum mechanics does tell you mathematical information about the path, and that is there. You have wave equations of quantum mechanics. They call Maxwell equation for light, or Schrodinger equation, which is coming later in the course. For electron, you mathematically solve it, and in the formula, you can substitute any value of x, any value of 2, even in the path. So mathematically the formula is there, wave function is called, for the path. So quantum mechanics says this wave function, which is wave, which is traveling, but it's not, if you have not done experiment, you are actually not seeing in the path, just for comparison. What you are seeing is only when it's detected here, and when it's detected, it is a probability, and the probability is detected or seen as set of dots, and every dot is a particle. So the traveling was a wave and strikes is a particle. Now I take you back, and there you see, if you are disappointed that we don't know anything about path and we don't know which path, which slit it passed through, then apparently your disappointment is reduced, apparently, but actually not. We can know about path, but is crucial. You have to pay attention to it. You can know about a path if you see the path. Now this logic lesson you can first take in the case of ordinary daily life. For a light coming through a window, you can see light in the path, but if you see the path, here the seeing means you have a dust particle and the light falls on dust particles, and wherever it falls, you detect, and because there are detections here, so you see the path. That is just one way of saying it, that if you see, you see. If you see the path, your predictions are accordingly. That should be generally logic as well, but at least in quantum mechanics, it's very clearly said that when you make prediction, you don't say that reality is there and whatever it happens, we make a prediction. No. You have to tell what experiment is, and then accordingly you make prediction. Now, if you see during the path, if you have a detector during the path, you have seen it, and you have seen it, that means you know it. You know which path it followed, and that means you know which slit it passed through. If you have seen it. But remember, so we got the answer, but you have to pay attention to it. We have not got the answer for the previous question. It's a different experiment, it's an answer, we know the path, but it's an answer to a different question, different experiment. So now I have to repeat that thing in the next slide. That in case of electron, detection is not done by dust particles, it's done in this way, and you have to here imagine it's a three-dimensional situation, and it's very difficult, if not impossible, for me to picturize it, so you have to imagine with me, pay attention to it. It's an electron source, its electron is traveling, its a wave is expanding, but you should get used to. It's traveling, it's a particle is traveling, it's traveling as a wave. Now here people say that, no, here the idea is that it's a photon. Photon is, how should I say, that is between, I can say this between me and this screen. And what is say, perpendicular to the screen, perpendicular to the paper, out of the screen, you imagine, towards me. Here it is, from here, that is going, you see. Here is a bulb, light source, and light source means a photon. And their photon wave is there, that went to, now it's on screen. And from the other side, you know, it's a photon wave from here, and electron wave from here, and two waves interact. Now you may like the word scene, but I think the actual quantum mechanics says interact. Two waves interact, and the wave is modified. Now it's a different wave. I have colored it differently. Now we will see it effects of this wave, they are dots. And now because if just before, maybe nanosecond before, a computer can resolve that. If a dot, just before dot, this flash appeared, we have reason to say that it is because of this wave, and the wave which has come now, it was originally from here, both slits, but now it is from slit 1. So if effects is a particle, that particle has come from slit 1. We know it. So you may be wondering that last slide I said we don't know, and now we say we know. And the difference is that we know answer, but we know answer to a different question. You know, I've changed experiment in previous slide compared to this slide. So answer is there, but answer to a different question, to a different experiment. And if you are now you think that this has told you answer to the previous, when it was no detector, then you pay attention to it. It's not, it does not tell you anything about previous experiment, because their experiment is different, and now experiment, in this experiment, not previous, interaction of this wave and this wave, you can say this particle or this particle, it matters, doesn't matter. It results a flash. Flash means an interaction is appear, and that will modify the wave. And this modified wave function, the effects you see, and that will tell you which path is followed, but this is an answer only when you put detector in the path. But that does not answer what the path was followed when there was no detection. You know, so our measurement changes. Now this is not a new lesson, an intermediate level as well, American high school level. people say it when they have to explain teachers, etc., and quantum mechanics uncertainty principle, they use this language. If the particle is there, when you measure its momentum, its position changes. It's there. Its measurement changes. Position is also wave function. Measurement changes wave function. So that's the old saying, is an example of the same. Another way of people like to say is that it was a wave when you measured it. A wave you did not know which path to follow. It was a wave. When you measured it and you know it's a slit one, people like to say it has become particle. It's their way of saying it. It's between you and them. I just remind you that it's people, those who say that, which is, I'm afraid, I don't think it's a very accurate language. It's not a particle, it's still a wave. But whatever it is, at least I can point out that this thing which I don't like to say, but those who say that, they are trying to say the same thing which I think I have said in a better way. My claim is, people say that same thing in something like a fancy language, which I don't like very much, but at least you can see that what they are trying to say. But I don't appreciate that, their trial, their effort. I think the better is honestly what I've sold, and I think that is better than many popular sentences, which I think there can be at times misleading. At least the last one. Before everything, I think you can take it. Okay, now the question is that measurement. People like to say scene or conversion or whatever it is. I would like to say measurement. So measurement changes. That means measurement, so much so that some people like to say that a particle is converted to, a wave is converted to particle, which I don't like. But I have told you other ways of saying it, that a measurement has effects. Now the last topic is that those effects of measurement, whatever you call it, however you describe them, are they reversible or not? And the answer is they are not reversible. What happens is permanently happened. Now the details of this sentence are 2 slides, and I start with one. That a wave function says that detection can be anywhere. So that means anywhere detection is a possibility. Detection can be anywhere means there can be many possibilities. But when you actually measure, it's somewhere detection appears. So out of that thing is selected, suddenly selected. Well, that is called collapse. It's suddenly selected out of all many possibilities. There were possibilities, and now after measurement, before measurement there were many possibilities. People say it was a wave. After measurement is only one place, and people say it is a particle. And that's why they say wave is converted to particle. But logical lesson is that out of many possibilities, only one is selected because of observation. Now, in itself, that's not totally new. It happens in a simple case of dice as well. Before throwing, you have 6 possibilities, and for example, number 3 appears. So, out of 6 possibilities, only one is selected. So, apparently, I'm saying that there is no puzzle, but actually, I have to clarify in the next slide. The puzzle remains, but it's not as big. There are 2 things I have to say. It's not as big as is normally thought. That's one thing. Another thing is that people say that I have seen a list of puzzles of quantum mechanics. 5 puzzles, maybe even more than puzzles. And the base of these discussions, because some big physicists have said something like that. Feynman said that nobody understands quantum mechanics. Feynman is a big name in a quantum mechanics, but he says nobody understands quantum mechanics. That means there's a puzzle. And I say puzzle is only this wave function collapse. And then Bohr said that if you are not shocked by, Bohr is also a big name in quantum mechanics advocation against facing Einstein. And he said that if you are not shocked by quantum mechanics, that means you do not understand. Now the shock is a puzzle, and I say, following these, you have seen on YouTube or so, I've seen it, a list of 5 puzzles and 6 puzzles, and so I think that's all. I don't agree, at least I should not say much about others. If they are 5, okay, they are 5, but actually there are 5 ways in which the same puzzle appears. They are not 5 independent puzzles. It's just only one puzzle. What I say, suddenly change, okay. If it is a puzzle, then yes, suddenly change. It's a puzzle, how it's suddenly. It's called wave function collapse. Now, to coming to that thing that I have compared with dice, so do I mean to say that there is no puzzle, but I clarify, no, still puzzle is remain. The difference is there are non-trivial differences between dice and quantum mechanics. In case of dice, we know that its forces are there and Newton's second law obeys that. The only thing is that there are many forces and we cannot solve Newton's second law. That's why practically we don't have any information. But in principle, we know equations. We know mathematics we have to do. We are not able to do this mathematics. But we know which mathematics we have to do. If mathematics in principle done, you know which side will appear. You can predict it. Practically you cannot predict it. Another feature of relevant feature of dice is that in case of dice, if suppose it's settled at 3, I shown you, but before settling it's moving, continuously moving, and you can see its motion. But in case of quantum mechanics, you know, if you do not put any detector in the path, then you do not know what happened before settling down. You have to just accept it. Only you know that. That's it. And we are not, human beings are not psychologically comfortable with it. We only like to think about path. But if you have not seen it, forget it. You don't know. You have not seen it, you don't know. So that, but you see it. When you detected. Before seeing, there were many possibilities. There are many. In case of dice, there are 6. And here they're continuously infinite. But when you see, when you detect, and you detect only here, if you detect only here, then out of these only one will be selected. And selected is the word collapse, and that's a puzzle. Okay, that I agree. This difference is there. You can't tell, you don't know about anything about motion, so you can't tell which possibility will appear. Only observation will tell you where it appears. Okay, that is the puzzle, and that I can't deny. That one puzzle is there. Okay, last thing I have to say that there were many possibilities, and they suddenly you can say change to one. This is an effect. Is the effect reversible or not? And the answer is it's not reversible, and that I've just shown you this way. That before measurement, you had many possibilities. You know, I take you back. There were many possibilities. And I've made it maybe hopefully simple one. I've shown you 4 possibilities, which is the intermediate case. In case of dice, you have only 2 possibilities. And here you have infinite number of possibilities. And here I've shown you 4. Every possibility has some probability, 10%, 20%, maybe 35%. And you can calculate that, but the total has to be 100%. Now, probability means first experiment. First is only a small number. For small number, there is no pattern. You don't know where it will appear. Suppose it appeared at 4. That's it. You have observation told you 4. You have to say 4. Now, in this system, if you do further experiment, it will be always 4. So now the probability structure has collapsed. After this measurement, it's always 4. If it happened to be 4, if it were 2, it would become 200%. If 4, it's a 400%. That's permanently. Before that, there's a language you should learn which is to be used in the next lecture, which is the quantum mechanics uncertainty principle related. Before measurement, you had uncertainty principle of quantum mechanics. After measurement, there's no uncertainties. 100% one. It's uncertainty is collapsed. Is finished, and that's the conclusion. That like any wave, probability wave can pass through 2 slits, but it's a probability wave, so it's seen as dots and dots. You can say particle, and seen can be. I showed you 2 experiments. One was no detection in the path. Seen was only a screen, or in the second, when through flash we saw during motion. But generally I tell you, seeing is not necessarily by an experiment or by seen, or seen mean any human activity, or no, nothing like that. The only thing is that there was a wave of electron wave that we tried to see through light, and we human beings through see light. But actually it's not a property of human being, it's a property of light. Light is a photon, and the electron came and they interacted it. And interaction has an effect, which was topic of this, and the effect is irreversible. So that's all in this. So next lecture onward, the topic would be more mathematical. That this probability, I said you can calculate probability waveform. You can solve wavification and square and probability. How to do mathematically? That's the next topic. And see you then.